Have you ever looked up at the night sky? Have you ever felt a sense of wonder, a sense of awe at the sheer scale of it all? We live on a tiny, fragile planet. It is a speck of dust in the vastness of space. Our sun is just one star among billions. Our galaxy is just one among trillions in the observable universe. We often think about how it all began. The Big Bang, a moment of incredible energy and creation, a moment that set everything in motion. But have you ever wondered how it will all end? The universe is not static. It is constantly changing. It is expanding. Edwin Hubble showed us that distant galaxies are rushing away from us. It was as if the entire fabric of space was stretching. For a long time, we thought this expansion was slowing down. Gravity should act like a brake. We thought the universe might one day stop expanding, maybe collapse in a big crunch. But something unexpected happened in the late 1990s. Astronomers looked at distant supernovae, exploding stars, cosmic lighthouses. What they found was astonishing. The expansion wasn't slowing down. It was speeding up. The universe is accelerating. Something is pushing everything apart, overpowering gravity on the largest scales. This discovery was so profound it won the Nobel Prize. It changed our understanding of the cosmos forever. This mysterious force, this anti-gravity, was given a name: dark energy. It is dark because we cannot see it. We cannot detect it directly. We only know it exists from its effects on the universe. It is energy because it's causing space itself to expand faster and faster. This discovery opened a new chapter in cosmology, a range of possible futures. Some are cold and lonely, but one is violent and spectacular. A future called the Big Rip. So what is this dark energy? The honest answer is, we don't really know. It is one of the biggest mysteries in all of science. It seems to be woven into the fabric of space itself. An invisible energy that is present everywhere. Even in the empty vacuum between galaxies there is energy. And this energy has a strange property. It has a kind of repulsive gravity. Instead of pulling things together, it pushes them apart. It is a constant, persistent pressure, driving the universe to expand at an ever-increasing rate. It's a cosmic accelerator pedal stuck to the floor. Think about it this way. Imagine throwing a ball up into the air. You expect gravity to pull it back down. Now imagine that as the ball gets higher, it starts moving faster and faster away from you. You would be baffled. You would know some strange, unseen force must be acting on it. That is what astronomers felt when they saw the universe accelerating. Dark energy is that strange, unseen force. It makes up about 70% of the total energy and matter in the universe. Everything we can see makes up less than 5%. All the stars, galaxies, planets, people. We are just the cosmic froth on a vast, dark ocean. This discovery poses a huge challenge to our theories of physics. Our best theory of gravity, Einstein's general relativity, allows for the existence of something like dark energy. Einstein himself proposed it as the cosmological constant. He later called it his biggest blunder, but now it seems he might have been right all along. When we try to calculate how much energy there should be using particle physics, we get a number that is outrageously, stupendously wrong. It's a discrepancy so large it's been called the worst theoretical prediction in the history of physics. This is where the Big Rip theory comes in. The future of the universe depends on the nature of this dark energy. If it is changing, it could be getting stronger. This more potent form of dark energy is sometimes called phantom energy. If this is the case, it will start to tear apart the very things held together by gravity and other forces. It will lead to a dramatic and definitive end for everything, a final, violent unraveling of the cosmos itself. The story of dark energy begins with a simple question: what is the fate of our universe? For most of the 20th century, cosmologists believed the answer lay in a cosmic tug-of-war. On one side, the initial outward push from the Big Bang, flinging all matter and energy outwards. On the other side was gravity, the universal force of attraction, pulling everything back together. Scientists thought the entire future of the cosmos depended on which force was stronger. Would the universe expand forever, getting colder and emptier? Or would gravity eventually win, pulling everything back into a final, cataclysmic, big crunch? To find the answer, Two independent teams of astronomers set out on a monumental task in the 1990s. They were the Supernova Cosmology Project and the High Z Supernova Search Team. Their plan was clever. They would use a specific type of exploding star, a type Ia supernova, as a standard candle. So, by measuring how faint they appear from Earth, we can calculate how far away they are. By also measuring their redshift, how much their light has been stretched by the expansion of space, the teams could map the history of cosmic expansion. They were trying to measure the exact rate at which gravity was slowing the universe down. As the data started to come in, something felt wrong. The results were not just a little off, they were completely backwards. The most distant supernovae, the ones that showed us the universe billions of years ago, were much fainter than they should have been. This meant they were much farther away than predicted. The only way this could be possible was if the expansion has been speeding up. It was a discovery that shook the very foundations of cosmology, a true eureka moment. Imagine the shock of those scientists. They had set out to measure one thing and ended up discovering something entirely different. The universe was not coasting or slowing down, it was accelerating. This meant that some mysterious repulsive force was at play, a force that was stronger than the collective gravity of all the matter in the cosmos. This unknown entity was given the name dark energy. It was a placeholder, a name for our own ignorance, but it pointed to a new, fundamental component of our universe, one that would dictate its ultimate destiny in the most dramatic way imaginable. The 2011 Nobel Prize in Physics was awarded for this incredible, universe-altering discovery. So we have a name for this mysterious stuff: dark energy. But what is it really? This is perhaps the single greatest puzzle in physics today. The simplest and most widely accepted idea is that dark energy is the cosmological constant. This was an idea first proposed by Albert Einstein himself. He added it to his equations to create a static, unchanging universe. When Edwin Hubble later discovered the universe was expanding, Einstein famously discarded the idea, calling it his biggest blunder. But now it seems he may have been right for the wrong reasons. The cosmological constant represents the energy of empty space itself, a fundamental energy of the vacuum. According to quantum mechanics, empty space is not truly empty. It is a bubbling, frothing sea of virtual particles that constantly pop in and out of existence. This quantum activity could give space an intrinsic energy, and according to Einstein's equations, this kind of energy would exert a negative pressure, pushing space apart. This fits perfectly with what we observe. As the universe expands, more space is created. More of this dark energy comes into being, driving the expansion even faster. Here is the problem, though. While the idea is elegant, the numbers do not work, not even close. When our best theories are used to calculate how much vacuum energy there should be, we get a truly absurd result. A 1 followed by 120 zeros. This discrepancy has been called the worst theoretical prediction in the history of physics. It is a catastrophic failure of our current understanding. It tells us that we are missing something huge, some fundamental principle of nature that we have not yet discovered. Because of this massive problem, scientists have proposed other ideas. Perhaps dark energy is not constant at all. Maybe it is a new kind of dynamic energy field that fills all of space, something that can change over time. This idea is known as quintessence. Unlike the cosmological constant, quintessence could have different strengths at different times in the universe's history. This possibility opens up a whole new range of potential fates for our universe. And one of those fates, if dark energy grows stronger over time, is the most terrifying of all. If dark energy is not a constant, its destiny-defining property is its equation of state parameter, a value scientists call W. This W is a ratio of the pressure dark energy exerts to its energy density. For Einstein's cosmological constant, W is exactly -1. This leads to the steady acceleration we observe. The universe would expand forever, becoming cold and dark. A scenario called the Big Freeze. But what if W is not -1? What if it's more negative? -1.1, -1.2, -2. This opens a frightening possibility. This hypothetical form W-1 is called phantom energy. As the universe expands, phantom energy density would increase. As the box of space grows, the energy inside increases. That creates a runaway feedback loop. More expansion, more phantom energy, faster expansion. The runaway expansion becomes unstoppable. The repulsive force grows stronger over cosmic time. Eventually it overwhelms other fundamental forces. It would tear apart galaxy clusters, then individual galaxies, then stars and planets from their orbits. No structure, however tightly bound, would be safe. That relentless force is the engine behind the Big Rip. Phantom energy is highly speculative. It even violates assumptions like energy can't be negative. Yet we can't rule it out with current measurements. Observations of W hover near -1 with a margin of error. In that uncertainty window, the phantom menace lurks. If future precise measurements show W -1, even by a tiny bit, the fate of the universe would be sealed. Not a quiet, cold end, but a violent, total disintegration. For billions of years, the universe played out a predictable cosmic ballet. Gravity was the lead choreographer. It gathered clouds of gas to form the first stars. It pulled those stars together to build the first galaxies. It then herded those galaxies into vast clusters and superclusters. All the while, the initial momentum from the Big Bang was carrying everything outward. But gravity was always there, gently pulling on the reins, slowing the expansion down. We thought this was the only story. A universe gracefully aging. But dark energy has completely rewritten the script for the second act of the cosmos. The discovery was a profound shift. It means that about 5 to 6 billion years ago, a cosmic tipping point was reached. This was the moment when the repulsive push of dark energy became stronger than the attractive pull of gravity on the largest scales. It was a patient, persistent force that finally took control. And now, our universe is a runaway train. This acceleration changes everything about our cosmic future. Instead of a future where galaxies might one day slow their retreat, they are now moving away from us faster and faster. This is not because the galaxies themselves are flying through space like rockets. It is because the very fabric of space between us and them is stretching at an ever-increasing rate. It's like two dots on the surface of a balloon that is being inflated more and more rapidly. The distance between them grows at an accelerating pace. The consequences of this runaway expansion are staggering. As distant galaxies are carried away, their speed will eventually exceed the speed of light relative to us. Once a galaxy crosses this cosmic event horizon, its light can no longer reach us. It is effectively erased from our sky, lost to us forever. We are living in a special time, a brief cosmic era where we can still see these distant galaxies. But in the far future, the night sky will look very different. The accelerating expansion is creating a great and ever-widening gulf between galaxy clusters. Imagine the universe as a vast, dark ocean. The galaxy clusters are like islands of light and matter. In the past, these islands were slowly drifting apart, but now the ocean itself is swelling, pushing the islands away from each other with increasing speed. The local group, our own small collection of galaxies including the Milky Way and Andromeda, is a gravitationally bound system. For now, this local gravity is strong enough to resist the global pull of dark energy's expansion. We are our own little island of cosmic stability, but beyond our local island, the Virgo supercluster is being torn apart. The repulsive force of dark energy is beginning to overwhelm the gravitational ties. Over billions of years, the great cosmic web will unravel. The universe will become a collection of increasingly isolated island galaxies, each an oasis of matter in an endless expanding void. For any observer in the distant future, as galaxies beyond our local group cross the cosmic event horizon, their light will be redshifted into oblivion. They will fade from view. Eventually, the sky for a future astronomer will be almost entirely black. Beyond that, nothing, not a single other galaxy will be visible. This leads to a strange and lonely thought. Future civilizations in our galaxy might look out into the darkness and conclude that they are alone in the universe. They would have no evidence of other galaxies, no hint of the Big Bang or the expanding cosmos. The crucial evidence would have been carried away. They would live in a universe that seemed static and empty. We are privileged to live in a time when the history of the universe is still written in the sky, a history that dark energy is actively erasing from sight. The effect of dark energy is not just on the space between galaxies, but on space itself. It is an intrinsic property of the vacuum, a pressure that causes it to want to expand. Think of it as a constant low-level tension. Right now, this effect is only noticeable over immense distances, on the scale of millions of light-years. On smaller scales, like within our solar system, or even within our galaxy, the force of gravity is overwhelmingly stronger. The subtle push of dark energy is utterly insignificant here, but the very nature of dark energy suggests this might not always be the case. If dark energy is a cosmological constant, its energy density remains the same. This is why it eventually came to dominate the universe. It is a patient force, but it will never be strong enough to unbind smaller objects like stars or planets. However, this brings us back to the crucial question of phantom energy. If dark energy is not constant, the story changes completely. In this scenario, the energy density of dark energy increases over time. The repulsive force it exerts would not remain a subtle background effect. It would grow. It would begin to challenge gravity on smaller and smaller scales. First, it would dismantle the galaxy clusters, then the galaxies themselves. The final frontier of its influence would be the tightly bound systems that seem so stable today. This is the central idea that leads to the Big Rip. The relentless growth of phantom energy means that no force will be able to resist it forever. The space within our own galaxy would start to expand, pushing the planets away from the sun. Even the space within the Earth itself would begin to expand, tearing our world apart. The very fabric of space becomes an agent of destruction, a force that will not stop until everything is torn to shreds. So, how do we get from a gently accelerating universe to a violent, all-consuming Big Rip? As we've seen, the simplest explanation is the cosmological constant. It leads to a future where the universe expands forever, getting colder and lonelier. It is a quiet, passive end. But what if dark energy is not constant? What if it is something more sinister, something that grows in strength over time? Enter phantom energy. Phantom energy is a hypothetical form of dark energy, far more aggressive than the cosmological constant. Its defining feature, its energy density increases as the universe expands. This is completely counterintuitive. Phantom energy does the opposite, a terrifying feedback loop. The more space expands, the more phantom energy. The more phantom energy, the faster space expands. A runaway process without a break. First proposed by Caldwell, Kamiankowski, and Weinberg in 2003. They explored a universe dominated by this substance. Its repulsive force could become infinite. It would overwhelm gravity, then the electromagnetic force, and finally the strong nuclear force. They named it the Big Rip. Phantom energy is, for now, purely theoretical, but we cannot dismiss it. Current measurements can't rule it out. The possibility remains that dark energy could be a growing menace, a phantom menace gathering strength to tear reality apart. The Big Rip is what happens if phantom energy is real. To understand the Big Rip, we need to look at a single, crucial number. It is a value that cosmologists call the equation of state parameter, W. This number sounds complicated, but it is simply a measure of how dark energy behaves. This one number holds the key to the ultimate fate of our universe. For a universe filled with normal matter, W is around 0. For a universe filled with light, W is 1/3. For the simple cosmological constant, W is exactly -1. But the Big Rip scenario happens if W is even slightly more negative than -1. Imagine if WW is -1.1, -1.5. This is the mathematical signature of phantom energy. A value of W less than -1 is what allows the density of dark energy to grow. It is the trigger for the runaway feedback loop. The more negative the value of W, the faster the phantom energy grows, and the quicker the Big Rip arrives. So, one of the most important jobs for astronomers today is to measure the value of W as precisely as possible. They are hunting for a number. Think of it like the pressure in a boiler. If the pressure is stable, the boiler can run forever. But if the pressure is slowly but steadily increasing, the boiler will explode. That is the Big Rip scenario. It changes dark energy from a passive feature of the cosmos into an active agent of destruction, Current observations from missions like the Planck satellite and the Dark Energy Survey have pinned down the value of AW to be very close to -1. However, there is still a small margin of error. It is within this tiny window of uncertainty that the phantom energy hypothesis lives. It is entirely possible that W is actually -1.05. This is why cosmologists are so focused on building better telescopes, to find out for sure what kind of universe we live in. Okay, so the Big Rip theory isn't just some vague idea. It's actually rooted in the solid mathematics of Einstein's theory of general relativity. The math actually shows that the scale factor of the universe grows to become infinite in a finite amount of time. That means there's a definite date when the universe will become infinitely large. This is the Big Rip. As that final moment gets closer, the expansion of space becomes unimaginably violent. The key idea here is that this force eventually becomes strong enough to overcome all the other forces of nature that hold things together. First, it goes after the biggest structures. The great superclusters are the first to go, dissolving as their member galaxies are flung apart into the void. Next, this phantom energy comes for the galaxies themselves. The space inside the galaxy will start expanding so quickly that the galaxy's own gravity just can't handle it. Our own Milky Way would be ripped apart. The night sky would turn into a sparse collection of lonely runaway stars. But the destruction doesn't stop there. The phantom energy's influence keeps growing, and its focus narrows even further. After tearing apart galaxies, it'll attack solar systems. The space between the sun and the Earth will stretch so violently that the sun's gravity just won't be able to hold on. The Earth and all the other planets will be ripped away from our star and flung into chaos. Every planet would become an orphan, cast adrift in the final terrible storm. The last stages of the Big Rip are, honestly, the most terrifying and profound. After dismantling gravitationally bound structures, it turns to objects held together by the electromagnetic force. Their substance is bound by chemical bonds. But even this incredibly strong force can't withstand the rip. The space within the Earth will expand so violently, our planet will explode. The destruction accelerates. Minutes before the rip, stars, planets, will disintegrate into basic atoms. The sun will be torn apart. The atoms that once made up our world, our bodies, everything we've ever known, would be scattered into an expanding soup. The universe becomes a sea of unbound atoms. Every object would be obliterated. But the Big Rip goes even deeper. In the last fraction of a second, phantom energy overcomes the strong nuclear force. When the rip exceeds the strong force, atoms are torn apart. Protons, neutrons, break down into a plasma of quarks and gluons. The building blocks of matter are ripped asunder. The universe stops containing matter as we know it. Then, at the very last instant, the Big Rip arrives. The scale factor becomes infinite. Phantom energy density becomes infinite. The laws of physics break down completely. Space-time itself stops existing in any meaningful way. It's the ultimate end. Total, fundamental disintegration. Every single particle becomes infinitely separated from every other. The story of the cosmos ends in a final, violent disintegration. If the Big Rip is really our destiny, don't worry. It's not happening tomorrow. The timeline for this cosmic finale actually stretches over billions of years. Let's assume a hypothetical scenario where the Big Rip is set to happen about 22 billion years from now. For the next few billion years, life in the universe would go on pretty much as it does now, only noticeable to astronomers. The first real signs of doom would show up on the largest scales. About 1 billion years before the rip, the phantom energy would get strong enough to challenge gravity's hold over galaxy clusters. The Virgo supercluster, which is our own cosmic neighborhood, would start to dissolve. Its member galaxies, once bound together, would begin to fly apart, each one starting a lonely journey into the ever-expanding void. As the countdown keeps going, around 60 million years before the final moment, the Big Rip would come for individual galaxies. Our own Milky Way would be its next victim. The phantom energy would overwhelm the gravity that holds our galaxy together. The beautiful spiral arms would be unwound and flung into darkness. The familiar band of the Milky Way in the night sky would vanish, replaced by a chaotic scattering of individual stars, each one isolated and cast adrift. With our galaxy dismantled, the phantom energy's focus would narrow even more. Just 3 months before the Big Rip, the space within our solar system would be expanding so violently. The Earth would be ripped from its orbit. All the planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, would be flung away from our parent star. Every planet would become a rogue world, hurtling through the final chaotic moments of the cosmos. The final stages of the timeline are honestly shockingly swift. Galaxies ripped apart, solar systems unbound. About 30 minutes before the rip, the Earth, now a cold, dark orphan planet, would meet its end. The fabric of space within the planet itself would begin to expand. The planet would be unable to hold itself together. It would explode, disintegrating into a cloud of its constituent atoms and molecules. This fate is not unique to Earth. Every planet, every moon, every asteroid, the stars themselves would suffer the same destiny. Our sun would be destroyed. The immense gravity that holds a star together would be no match for the phantom energy. Every star extinguished, the universe goes dark. Destruction now at the atomic level, a thin, expanding soup of individual atoms. But the Big Rip is not finished. With about 10 to the power of -19 seconds left on the clock, the phantom energy breaks the electromagnetic bond, electrons ripped from nuclei. Every atom that ever existed, ionized and dismantled. All structure, all complexity, all chemistry would be erased in an instant, broken down into more basic parts, a featureless plasma of fundamental particles, rushing apart at impossible speeds. So we've reached the last truly infinitesimal fraction of a second. It targets the strongest force in nature, the strong nuclear force. Even that power can't stand up to phantom energy. Atomic nuclei are torn apart, protons disintegrate, neutrons disintegrate, they split into quarks and gluons. The universe becomes a quark-gluon plasma, particles flung apart by relentless expansion. Matter as we know it ceases to exist. What happens at the very end? The moment of the Big Rip, general relativity predicts the scale factor becomes infinite. Phantom energy density becomes infinite. This is a singularity. Physics breaks down completely. We can't describe what follows. Time loses meaning. The fabric of space-time is torn. End of matter, end of energy, end of space, end of time. The most absolute end imaginable, not a rebirth, a final definitive conclusion. Every particle becomes causally disconnected from every other. Each one an isolated island. No structure, no information, no memory of the universe that came before. The Big Bang, the rise of life, consciousness, erased. A sobering reminder that our universe might be destined for a final, violent unraveling. The Big Rip is more than just a physical theory. It represents the ultimate erasure of cosmic history. Think about how we've pieced together the story of our cosmos. We look at the light from distant galaxies. We study the cosmic microwave background radiation. Our universe is rich with evidence of its own history. The Big Rip would be the equivalent of burning this entire archive. In the final moments, as every atom is torn apart, all information is destroyed. The very patterns and structures that encode information would be obliterated. The atoms that once formed your brain would be scattered. The planets that held the fossil record would be vaporized. The light from distant stars would be lost. The Big Rip is not just the end of the future, it's the retroactive destruction of the past's meaning. It's the ultimate cosmic reset. This has some pretty profound implications. Humanity's entire journey, all of our art, our science, our love, our struggles, would be rendered utterly transient. There would be no legacy, no ruins to be discovered, no message in a bottle. There would be no sea left. The Big Rip suggests a universe that is ultimately finite. Our existence would be a fleeting flicker, a brief cosmic springtime before an eternal violent winter arrives. This idea really challenges our deep-seated need for permanence. We build monuments, write books, create art, in the hope that something of us will last. But the Big Rip offers no such comfort. It presents a cosmos that is ultimately hostile to memory and structure. It forces us to confront the idea that the universe may not have a grand purpose or a lasting legacy. It simply is, and then, in a final terrible moment, it simply is not. The prospect of the Big Rip really forces us to ask some of the deepest philosophical questions. If the universe is destined for total annihilation, what is the meaning of our existence? Why should we strive, create, explore if it's all going to be ripped apart? Some might find this idea profoundly depressing. But there's another way to look at this. Maybe the finite nature of the universe makes our existence even more precious. If our time here is limited, as individuals, as a species, as a planet, as a universe, then every moment becomes infinitely valuable. The beauty of a sunset, the joy of discovery, the connection we feel with others, these things aren't diminished. Their transient nature might be what makes them so beautiful. A story doesn't need to go on forever to be a good story. Its meaning is found in the journey. This perspective can actually be empowering. It suggests that meaning isn't something given to us by the universe, but something we create for ourselves. We are the universe's way of knowing itself, even if just for a brief cosmic moment. Our consciousness is a remarkable and rare phenomenon. We are the custodians of this moment of cosmic awareness. Our purpose is to live fully and to understand as much as we can within the time that we have. Ultimately, contemplating the end of everything brings us back to the present. What is real is the here and now. The knowledge that the universe might end so violently can serve as a powerful reminder of the fragility and beauty of our current existence. It urges us to cherish our world, to solve our problems, and to continue our quest for knowledge. Because in a universe that may one day be torn to shreds, the act of asking the question, how will it all end, is in itself a profound and meaningful act. Our journey to the end of time leaves us standing at the edge of a great mystery. The Big Rip is a startling, dramatic possibility. Whether the universe ends in a violent rip, a cold freeze, or a fiery crunch all depends on the true identity of this dark energy. It's the great unknown in our cosmic equation, and scientists all around the world are in a race to solve it. To find the answers, we're building ever more powerful tools to gaze into the deep cosmos. Telescopes like the European Space Agency's Euclid mission and the Vera C. Rubin Observatory in Chile are designed specifically to map the universe. They'll observe billions of galaxies, measuring their distances and how they're distributed. By studying the history of cosmic expansion in minute detail, these projects will help us pin down the value of W. They're trying to figure out if it's a simple cosmological constant or if it's the more menacing phantom energy. But the mystery of dark energy is so profound. It might require a revolution in our understanding of fundamental physics, a new theory of gravity, or a deeper understanding of the quantum world. The puzzle of dark energy connects the largest structures with the tiniest subatomic particles. Solving it will likely require a unified theory of everything. For now, we live in a moment of profound uncertainty and wonder. But the question of how it will end fascinates us. It drives our curiosity. Contemplating these cosmic endings reminds us of our own small but precious place in the grand scheme of things. We are a part of a universe that's full of mystery, a universe that we've only just begun to understand. The quest to know our cosmic destiny is a journey that continues, one discovery at a time, as we look up at the sky and ask the biggest questions of all.